Good morning, one and all. I think Keshav already introduced me. I work in solid state NMR area. I'm an associate professor in Alva Institute of Engineering Technology in the South Canara belt. Actually, I am originally from Bangalore. All the way from Bangalore, we went to South Canara, where I got the opportunity to do my research as well as teaching over there. So we have established a lab over there with the help of departmental HOD Dr. Ramprasad AT, who has been wonderfully given me okay, as a scaffolding to build the lab and all. With the good grant of 30 lakhs, we have procured instruments. Shortly, I will be talking about it. Thanks to Gurumurthy sir, who introduced the Krishnavani ma'am, and we have been collaborators and a couple of work. And thanks to ma'am, organizing committee, for inviting me and thinking that I'm a eligible guy to present here. So probably I will present my knowledge or information, share with you, and probably we can learn and unlearn together. Because the whole idea of the workshops is to fine tune ourselves, how to better teach, how to better understand, and learn and unlearn, and many things will be there that we are supposed to do. With this brief idea, so what I will be talking about, we have a good NMR understanding from KJM's talk, that is, we call him KJM, Dr. Mallikarjunaya, who gave a brief introduction about what is NMR and also solid state NMR. He has been my mentor and senior in IISc in Bangalore University also. So follow up talk, this one is good thing that it's very difficult to follow up like stalwarts like Gurumurthy. Gurumurthy sir, I think it's very difficult to follow him up, but still I'll fill his shoes, try to do it. My area of research is solid state NMR and also paramagnetic system. Why paramagnetic system? Shortly we will see. When the thing paramagnetic comes into picture, the whole NMR fails. Why we will be shortly seeing it. Because NMR wholly relies on carbon and proton shifts or any chemical shifts. But whenever you have paramagnetic systems like copper, nickel, or any transition metals, or let's say radicalic materials, the whole NMR fails down. That's the reason I call it as a fiend. Fiend is an evil spirit. Fiend is an English word for evil spirit. It's just exactly opposite to friend. It is almost are missing. Fiend. Fiend is an evil spirit. NMR works on the idea of pulse and delay. Pulse and delay. Simple, it is a RF pulse and a small delay where you capture the interaction time. So if you are working in molecular level idea, then molecular spinning, you capture interaction. Yesterday, KJM was talking about, Mallikarjunaya was speaking about rhodospin. Any protein which wobbles or rotates, small interaction time, physicist will capture using RF pulses. So short delay. So it's about the pulse and delay, two ideas. But now you have a fiend, that is basically evil spirit, which is paramagnetic. When paramagnetic component comes into picture, then whole NMR fails. So how we can tackle? There are a lot of chemists or probably physicists and chemists. They might work with transition metals where you have unpaired electron. There might be a metal, there might be insulator or semiconductor, but there should be a paramagnetic. If they come into picture, then how you go about with NMR? That is the whole idea. And I call it as a spin choreography. Famously, Richard Ernst used to talk about it. Richard Ernst is one of the inventor of Fourier transform NMR. I had an honor to interact with him and spend most of the time in the research, so-called conferences. Short interval of time we used to get, and he was an amazing individual. So I had a photograph I can just show you later. And lot of NMR people we worked with. Because of them, we inspired ourselves. They used to say directly. It was very scary statement. They used to say, "Remember, gentlemen, you are working in NMR. NMR is no more research, not nuclear magnetic resonance. So you have to make yourself need more research. You have to go for need more research." So anyway, the point is we will be applying for smart materials and proteins. I will not be talking deeply into that, but I will be giving you a glimpse of where your problem, your personal project problem or your problem, where you can think you can apply solid state NMR. Okay, so that is I will be talking about, giving some of the examples. Lithium tin intermetallics during my postdoc days, sodium metal oxide battery applications, where I was in Bordeaux with Madhu as well, and viologens in PhD time, and copper cyclone, which was because I'm a methodologist. Okay, I'm an experimentalist basically, but the notion of experimentalist has completely changed as I came to India. I purely worked on calculations, DFT calculation. People have a misnomer of me saying as a theoretician. I'm not a theoretician. So we'll be talking about that. Introduction to what is NMR, solid state NMR, techniques, application, what are the accomplishments in solid state NMR people have done, solid state NMR of paramagnetic system, challenges, development, and so on and so forth, resultant discussion for some of the materials, and then finally conclusions. Now, in masters, I was very much interested in interaction of light with matter. There were very great teachers with me who inspired me to do work on this interaction of light with matter. Especially, we started off with Einstein E&B coefficient, very famous. The spectroscopist without this Einstein E&B coefficient will not understand what is spectroscopy. Whatever I am holding in my hand, the laser, that is due contribution to the Einstein E&B coefficients. The interaction of radiation with matter. Interaction of radiation with matter, interaction of radiation with it. Yes, it really matters. Interaction of radiation really matters. So, why? Because what is spectroscopy? Spectroscopy is a interaction of radiation with matter. It gives out the information about the material, whether it is ionic state, electronic state, vibrational, nuclear. So we can have different stages through your electromagnetic spectrum. It's a very basic slides to make you understand which part of electromagnetic spectrum I deal with. So I think it's very self-explanatory. Yeah. So start with X-ray spectroscopy. We can also have the microscopy, which is X-ray diffraction, gamma rays and all. X-ray spectroscopy, if you have an atom when an X-ray or a very high energy of X-ray kind knocks off an electron which is closely lying to K shell, M shell, L shell, then you can get the information about the material. Meaning you can actually have a percentage of gold, percentage of silver, oxygen, all these things can be done with a basic setup. Now we have handheld XRFs, X-ray fluorescence, where you shine X-ray XRF material or XRF instrument handheld, you can have the composition. Let's say for example, I have a watch, I tell that it is 100% some material, 90% this material, something like that. If they shine the XRF, easily you can say directly. So, which part of the electromagnetic spectrum? X-rays. Now, then we comes, okay, little bit shorter frequency or like lesser frequency, UV visible. The high frequency, high energy, UV. UV interaction is ultraviolet. So, it talks about the interaction of valence shell electrons. So, it talks about the bonding, anti-bonding, how molecule is formed, mostly dealt with chemists, and of course physicists also work on the optical region and all. Electron transition happens, so all these things happen. UV spectroscopy, people have worked on this. Then comes the IR. So this is your instrument. We have the instrument back in AIT, Alva. So then we have IR. People use this right and left like anything every day. When they synthesize a material, they go for IR and they screen the material and try to see what is the material inside, the vibrations and all the check. They try to understand. We will be having a theoretical session where we have all these vibrations generated through DFT calculation. We can do that also. So that will be handled in the next session after a couple of sessions. So IR, vibrational spectroscopy, where you have a material, so it follows Beer's law. So amount of transmittance, absorbance, all this is well known. This instrument is also there back in my place, so in our lab. So it is one of the state-of-the-art instrument, FTIR. It can handle the liquid, it can handle the solid, gel, any kind of material. It's a very simple one. It's not the old technique like KBR pellet. Don't have to do all those things. Within a fraction of, let's say, 3-4 minutes, you can have, I would say, around 10-20 samples easily can be done quickly. So it is so fast. So IR is the one which contributes for the structural determination. Next comes the NMR. NMR, all these things are the eyes for a human to understand the various levels, nuclear level, electronic level, so-called attributing for the structural information. Once you know the structure, properties can be understood. Structure property correlation is the way to go about. You change the property, then structure changes. You change the structure, property changes. This structure property correlation is all we want. NMR is seriously spoken. It is nuclear magnetic resonance. 3 words: nuclear magnetic resonance. Since there is a word nuclear, it doesn't mean that any high energy is involved. All we look for, like KJM has already introduced to you, we require any unpaired nucleus. Meaning that in the nucleus we have protons and neutrons. Protons are positively charged particles. You have magnetic so-called species, that is protons. Neutrons are neutrally charged, but still you have magnetism due to the quantum mechanical idea of pinpointization. So you have this magnetic moment. So when they both are put together, they even out and they give 0. The nuclear spin is 0, I. But if I is non-zero, that is where NMR comes into picture. So NMR was developed during World War II. World War II, the whole world was at war, very difficult situation. They had amazing instruments like warplanes. They used to attack the enemy territory. They had this wonderful instrument, of course, radar. Radio wave detection and ranging. So they used to shine radio waves because longer the wavelength, you can so-called profile the so-called any objects which is of that particular fit into that wavelength. So they used to detect, they come back and they give the information. This is the idea of NMR brought into radar. Radar was the idea. So what is NMR? When you take a material, any material, it should be a magnetic species, non-zero nuclear, that is non-zero nuclear spins. You take it and when you put in a magnetic field, it undergoes something called as nuclear Zeeman interaction. So it starts to precess with a frequency called as Larmor precision frequency based on the gyromagnetic ratio. Okay, gamma is the unique for each and every element, whether it is hydrogen, oxygen, nitrogen, sulfur, anything, it starts to precess. So let's say, for example, if you take a material and start to put in a magnet of 1 Tesla, you have such amount of so-called frequency, around 42.58 megahertz, start to precess megahertz. So you can imagine that if you want to change the state of this nucleus, so that energy lies in radio frequency. Okay, so Larmor precision frequency, that frequency what you connect, that is frequency and the magnetic field, that lies in radio frequency. That is, if you put so much amount of radio frequency, then suddenly the nucleus, just like KJM puts in a right way, everyone are oriented towards me, and suddenly I want to I bring another magnetic field, everything is other way. If I put RF energy, it will flip. So this state of taking a parallel state to anti-parallel state, it requires some energy. That requirement is around RF. So when that is done, so you get a energy. So now that energy is a nuclear Zeeman interaction. In physics, we put in a very simple E is equal to mu dot B. So action of mu on B or B on mu. B is the applied magnetic field. Mu is your magnetic moment or magnetic field in your so-called your sample. They are very, very tiny magnetic moments. So B naught is very heavy, that is very high. Okay, high magnetic. And why there is a negative sign? Any answers? Why there is negative sign? E is equal to minus mu dot B. Because it's an interaction Hamiltonian. That is how you get the energy. Yeah, everyone knows what is Hamiltonian, right? Total energy of the system. So when you define Zeeman interaction, this is what is Zeeman interaction. Yeah, but when I put mu as n, that is mu, nuclear Zeeman interaction. Why there is negative? Any idea? Yeah. Energy minus sign. So it's got to do with the parallel state and anti-parallel state, opposite. So both of them are opposite in nature. It's not going with, it's against. That is the whole idea. That should be kept in point, because even in ESR we have electron spin resonance, that is also there. So just to bear in mind, if someone is really looking for that, please have a look at it. It's very important idea. Okay, as you already know, as magnetic field strength increases, your energy difference also increases. Meaning the very important question here is that if you have stronger and stronger magnet, you can have a well resolved state. Okay, otherwise you still in Boltzmann's state, that is KT 3 by 2 KT or half KT or overall 3 KT. That KT difference should be increment so that you have a good resolution. So you require a good magnet. Magnetic field is very, very crucial. What are the magnetic moments that you can use? You can have all the elements in the periodic table: red color spin half, orange color spin 1, quadrupolar, spin 3 by 2, spin 5 by 2. You have variety of them, but wherever your nuclear spins are 0, there is no business for NMR. So you should have nuclear paramagnetism. Everyone knows what is a paramagnetic. Paramagnetic means something which is having unpaired electron. Okay, unpaired electron. Okay, it can be a conductor also. You can have a poly paramagnetism and Curie magnetism also, paramagnetism. But I speak about unpaired electrons. If it is an insulator, you can talk in terms of Curie magnetism, and if it is a metal, you have a poly paramagnetism. We have worked in that area also. But the whole idea here is the unpaired electron is a crucial point. Now, when you have unpaired electrons, then that is a different story. But here it is nuclear paramagnetism. That is, there should be unpaired nucleus. That is, you have your protons and neutrons which don't pair up and there is no cancellation. I should be non-zero, greater than or equal to half. That is where NMR comes into picture. So you have the species, you can have various species. Now you have a brothers and sisters of these so-called elements, isotopes. You can have a proton, you can have a deuterium, you can have tritium, you can have a carbon 13, you have carbon 14. Carbon 14, can it be done? Carbon 12, can it be done? So you can think over just by addition and subtraction of all these values, addition basically. So you have phosphorus in your system, you can do NMR. Now what does NMR give? I still have not got to that point, but just we'll go slowly. Two people who attribute for this particular thing is Isidore Rabi and Stern, famous Stern and Gerlach experiment. Yeah, so molecular beam and all those things. So they gave this idea that NMR, or basically molecular beam, can be generated of it, anomalous Zeeman effect and normal Zeeman effect, all those attribution to them. So that is where it followed. So now applying a so-called your RF frequency, then it will flip, and that is how they got the very first signal in paraffin and water. This is your water signal. Just like you take a sample, put inside a magnet, it starts to precess. Wherever you have the quantization, that is, you have your magnetic field, it starts to precess. Now anti-parallel state, parallel state are split up, degeneracy is removed. Okay, then what you do is that you ignite their energy through sending RF. Why RF? Because we have already calculated using your basic Larmor frequency. Omega is equal to gamma B naught. What is omega? Omega is a time dependent factor. Yeah, time dependent variable. Yeah, it is time dependent. It is not a static field. It is a variable, time varying field. So your frequency, angular frequency, gamma is the nature of your material. Nature means your hydrogen, carbon, phosphorus is a gyromagnetic ratio. It is dependent on the intrinsic property of your material, meaning that element. So gamma of hydrogen is very high. Okay, natural abundance, naturally available. Okay, carbon is how much? Carbon 30. So all these things is your gamma. Based on gamma, your omega changes. Based on that, okay, this is with you. Okay, this is under your influence. You can increase and decrease. This is the nature of the so-called element. What element you are probing, whether it's hydrogen, carbon, phosphorus, whatever, and that is how you get your. So in NMR, you have two ways in which you can do NMR. You can either fix your frequency, which is not lying in gamma rays, X-rays, UV rays, IR, but it is lying in RF. Take a simple wire, connect it to power supply of AC, 50 Hertz, 200 Hertz, 300, you already generate your RF by connecting it to an antenna or an inductor basically. Yeah, that is how you generate your RF. Now shine RF, just like your radar, an aeroplane is coming, okay, or a plane is coming, you shine radio frequency, you gauge it by just sending it and it will return back. That is the same principle in NMR, same thing, there is no difference at all. Now here, E is equal to minus mu dot B, that is the main interaction, Hamiltonian. Now interaction is very, very crucial. What are the other magnetic field inside? That we have to care. Anyway, Richard Ernst even more precisely gave the idea here. Water signal, whatever first proton NMR water signal what you got doesn't give you any much information. It's just a proton signal, very low magnetic field, just one signal coming from a nucleus. It's simply amazing. During 1940s, some non-living thing is trying to speak to you. That is, here I am, water, here I am, somewhere I am. Is trying to communicate with your antenna, with your inductor. Water is speaking to you through your so-called CRO. That is amazing, simply amazing what you have this. But now, one step ahead, there are mathematicians, Fourier transform. So they applied, and of course there was a chemist, Richard Ernst. He said that instead of having fixing frequency and moving the magnetic field, or fixing the magnetic field and moving the frequency, let us all ignite all the frequencies altogether by putting RF pulses. So that is what he did. So while doing this, he got this amazing result. What is this result? Here you don't scan the whole signal at this point, that point, this point. So not like that, but all together when you scan, that is all together through RF pulses, because pulse is in terms of time. Short time, frequency will be time and frequency inversely proportional. So short pulses have a broad band frequency, or broader so-called time or large time has a narrow so-called frequency. So now you can excite all of them. You can choose the regions through your short burst of pulses. So it's just like your piano. Very example is piano. I have a scale, right? So re, ga, ma, pa, right? I'm having 100 hertz, 200 hertz, 300 hertz. I'm pressing each and every key, different notes, different frequency. Yeah, individual frequencies I'm scanning. But imagine I put all together. Yeah, I'm putting all the frequencies all together. You get a very karkash sound, right? Very horrible sound. But still you are exciting all of them together, right? It means that it is up to you how you deconvolute all the frequencies and do you do it. Yeah, that is how you do this. Now, why you are supposed to do that? Because if you take any material, if you fix, because NMR is all about fixing a particular nucleus, what you want to study. So let's say, for example, hydrogen and carbon in our Earth. I don't know about the alien planet, but our Earth, hydrogen, carbon, oxygen, nitrogen are the base components. If you study these, you can study anything. You take hydrogen and put in a magnet, 42.5 megahertz, something like that. You got in 1 Tesla magnet. You got a signal like this. But you think that there is only one signal? We don't know. So I increase my magnetic field. Even more it spins. Or so-called, you have two pictures. That is energy level diagram and so-called level diagram and so-called precision picture. So you can use either pictures to understand. So now what you do? You increase the magnetic field and so-called your Boltzmann's gap is even more far. And then you again put different frequency and start to see where all the things. If you take ethanol and you put in a 1 megahertz or so-called 42.5 megahertz, 1 Tesla, you get a simple signal, one signal. It doesn't say anything about it. But if you take the same thing and put in a very high resolution, this is how you get. Okay, I don't know exactly how much they acquired. Probably 100 megahertz spectrometer, sufficient, more than enough. I think it's around 2 Tesla, 2.5 Tesla magnet. So you have this 3 regions of same proton. I'm not changing any element. I'm just using the same element, putting hydrogen inside a magnet and it start to process. And what is it? It's a ethanol, C2H5OH. I take ethanol, put inside a magnet. Yeah. So what is ethanol trying to say? It's trying to say that I have 3 types of hydrogen, CH3, CH2OH, and I am lying at different frequency. Why different frequency? Because I am applying 1 Tesla. Imagine I am applying 1 Tesla and the base frequency of hydrogen you have already calculated. We have it. So just to go back and see. So just I wanted to show this. So for 1 Tesla, or let's say 2 Tesla or 1 Tesla, 42.58 megahertz. All the protons should circle around the magnetic field, 42.8 Tesla, right? But now you see here, yes, this scale is frequency. This scale is frequency or magnetic field, whatever you want, because this is the equation that follows. Now here, you should get only 1 signal, but I am getting 3. What is the meaning? You care to venture? Any question? Any answers? I am fixing the so-called element hydrogen. It has to have I am fixing the radio station. I'm fixing the radio station 91.1 megahertz. I have the same song, right? But I am getting other so-called signals also. What is the meaning? Meaning they are closely lying, right? So how I am getting this radio frequency? How do I get this radio frequency? How did I get radio frequency? Through fixing the magnetic field, right? Or how do I get the magnetic field? By fixing the frequency. They both can be done. Yeah. For 1 so-called Tesla, I have 42.8 megahertz as the base frequency for hydrogen. Hydrogen base frequency is always should communicate in 42.8 megahertz. But now I have splitting of 42.884, 42.881, 42. Very low. See where I am saying 42.88. I am not changing 40 megahertz, 41 megahertz, 42 megahertz. See what I am saying? 42.85 megahertz, 42.8512 megahertz, meaning what? My interactions are in kilohertz or hertz. Are you understanding it? 0.000 megahertz, meaning something is changing. I am putting 1 Tesla and all 1 Tesla is not reaching my nucleus. Okay, somewhere shielding is happening. Someone is protecting this so-called barrier, right? So there should be something called as anti-shielding. It can't be electric field. It can't be any other force, gravitation field, because gravitation field is several order less compared to the magnetic field. Those things. So it should be a magnetic field. So there is some other magnetic field inside your material. I'm talking only about nucleus. So what are the other magnetic field you can expect? Where all the magnetic field can be expected in a particular material? I have atom, I have nucleus. I'm only probing in the nucleus, nuclear magnetism. Where did I get the nuclear magnetism, by the way? Protons and neutrons, spin, okay? But where all I can get the magnetic field? In atom, I have nucleus, charge, particle, neutrons, neutrally charged. There is no neutral, there is no charge in that. So still it's contributing for magnetism. Okay, I have nuclear magnetism. But where all I can get the magnetic field, where it is protecting 1 Tesla, it's not reaching 1 Tesla, but it is 0.999 Tesla reaching, or 1.001 Tesla added. It can be both, by the way. Where is it? Very good. Electrons, simple. Electrons. Electrons, charged particle, everyone agrees. Everyone knows, right? Negatively charged particles, when a charge moves, you have very old concept. This classical idea. So you have your current. Current means you have magnetic field, all these idea. But strictly speaking, when you bring quantum mechanics, is a quantization, that is your magnetic field is ready. Now, the electron surrounding a material is basically stopping any applied magnetic field to reach there. Screening, we call it a screening. You are screening of. So basically, if I have a material, it is trying to screen in such a way, observe it, CH3, I'm only probing hydrogen. Don't get distracted by the carbon, yeah? Hydrogen, H3, okay? Structurally, it is very 3, H2, 2 hydrogens, OH. So are you finding it any difference? Difference is there? One is H, one is H2, one is H3, yeah? Some people who already know NMR, please, you can also answer. So what is this? What is changing? The electron so-called locality or so-called the neighboring things are changing, yeah? Now, if something is not exactly reaching, yeah, it means that something else is stopping, and who is stopping? The subtraction give you the shielding. So here, normally you should get a big hum, but why you are getting 3 different? Because 3 different environments, 3 different magnetic fields. You are giving 1 Tesla, but the amount of it is reaching there to your material. If it is purely proton sitting over there, okay, it's okay. But here it's not purely proton, addition of something and deletion, magnetic field. So that is giving you 3 different environments. This is the beauty about NMR, that it is giving you a chemical signature of the group present. It's more about the magnetic field, purely about magnetic field. I sent 1 Tesla magnetic field to the material, not completely reaches. Why? Because electrons surrounding it, and where the nucleus is, that will tell you, meaning it is telling the location. Not only location, it will tell you the surrounding also. Where I am, exactly where I am. So that will tell you 3 different environments. So this is well documented in NMR. So using this, we perform so many things. So many things. People work in metal organic systems, carbon, proton, all these things. Not only in carbon, we can have sulfur, we can have nitrogen NMR, any NMR where my spin I should be, nuclear spin should be not zero, non-zero, greater than or equal to half. Anything which is greater than or equal to half, we can do it. Is equal to half, more better. If it is greater than half, then it will become nuclear quadrupole. Another technique should be applied. But surely, it's well established. We know exactly where the proton comes, where exactly the so-called all these comes. We know exactly where the things are. So it can be applied in metal organic systems, MOFs, okay, zeolites, catalysts, and borosilicate glasses, and things like this. Biomolecular NMR, Mallikarjuna already told about this. Okay, so basically when you have a protein, whenever you have a material like beta receptors and other things in your diabetes or something control, so what is basically something which causes problem in our body is a protein attaching, or we call it as docking into something like another protein. So it either inhibits or exhibits. Inhibition means controlling, exhibition means something like it exhibits more its property. one of them switch off, another one switch on. So this kind of activity brings different diseases in our field. So if you want to study the structure, you can actually change the protein structure by docking and other things. So where exactly it is locating, all these things can be done this biomolecular NMR. And the other thing is that, so-called battery materials, I think many people have worked on it. I have also worked on it. So battery materials, lithium and sodium batteries. So basically wherever structure is there, we come into picture, NMRist. Now the problem is NMR is very expensive. So it's a white elephant. It's a ivory elephant, I would say. It's a white elephant because it's very, very expensive. So how much does it cost? It's around 10 to 20 crore. 10 to 20 crore. Even if you purchase that, the usage of this NMR is very difficult because maintenance is very expensive, high maintenance. Liquid helium filling, maintaining the superconducting magnetic field, because the magnetic field that we use is superconducting magnet, immersive superconducting magnet, lanthanum, gadolinium. I think there are combination of these superconducting magnets which we immerse into your so-called liquid helium and bring it to critical temperature and maintain it. All those things is there. Maintaining it is very difficult. Liquid helium, liquid nitrogen, we pour again outside the liquid helium so that we can protect the easily boiling off or evaporation of the so-called liquid helium. So we maintain that. So all these things are there. But there is also NMR which can be purchased in a very simple one. This we have in our lab, earth field NMR. If you compromise with the resolution, I told you why magnetic field is required, we'll shortly show. So why so much money, we'll see that shortly. So but we can purchase to a very smaller one, basic one. So 42.5 micro Tesla is the earth magnetic field. Earth expels magnetic field due to the iron core present in it. So you have magnetic field, use the earth magnetic field. Earth magnetic field is quite homogeneous, it doesn't change much, changes once in a million year or something. Whenever the changes of the so-called your axis, everything changes due to the movement of your earth crust and all those things. So it is quite reliable for at least million years. We use that earth field NMR. Mouse NMR is there, that costs around 10 to 20 lakhs. So we have this. Why expensive? Why so expensive? Why so much expensive money is put in? So it uses cryogens. What are cryogens? What are cryogens? Low temperature, so-called when you take a gas and compress it, 3 by 2 kT is equal to half mv square. Very simple equation. 3 by 2 kT is equal to half mv square. V, reduce the velocity, cool down. Simple. Very simple logic, yeah. So using that, we can use that as a fuel and cool down any materials. And of course, we have a lot of effects, a superconducting material. So you have this, and internal part of the NMR is superconducting coil. That is where sample goes. Precision matters, yes. Attributing for resolution. Why resolution? Have a look at it. Small ethyl alcohol, ethanol has 3 different signals. If you go for any other material where you want to immediately solve the issue, first, when you synthesize your materials, what characterization technique you go and first to find out structure. You don't worry about NMR, any other NMR, apart from another spectroscopy, apart from NMR spectroscopy, what are the other spectroscopic technique or any other? FTIR, that is a very basic one. But if you want to have a preferred structure, XRD is a very important, right? But can you do XRD on a powder? You can do, no issues, but the probability of getting the answers is very difficult, right? You have a big hump or small, tiny humps. We have a XRD person sitting over here, he can speak about it. So basically XRD is very difficult if you don't have any single crystal. Crystallinity is mattering, yeah. Whenever you don't have crystallinity, when you have amorphous, NMR is the way to go about. Because NMR not only give you the structure, it will take some time because we will have n number of experiments put together and we give the structure, but also we speak about dynamics, what Mallikarjuna was talking about yesterday. So you see there, during Corona time, Corona was understood in terms of this figure. The figure, it looks like very cute animal or something cute thing, but it caused a lot of problem. So what is this? Basically a small protein, protective protein called a spike protein. Spike protein is the one which used to attack your lungs, attach to lungs and also attack your body. The spike protein is the one. There is a protective layer for the corona. Corona was just eating away humans. It was just hosting, or it was just as a guest to a particular host, any host body attaching to a particular body through your spike protein. But if you get rid of this spike protein, corona has no value at all. Yeah. So this is a protein. So if you want to understand this protein structure looks like this. There are only three types of structures in proteins. Okay, alpha helix, beta sheets, and random coil. Very difficult. All three are very difficult. Alpha helix and beta structure are very simple, but random coil is very very tough to crack. And using the Ramachandran plot, which is very famous plot given by M. Ramachandran, physicist basically, and using NMR, he was an NMR guy in ISC. So Ramachandran plot gives you the idea of alpha helix, beta sheet, and random coil. What structure is your protein based on that torsion angle and all those things. So when the protein turns, it can act as a good thing. Okay, when the protein turns in the other way, it can act as a poison. So something like a cis and trans model in your chemistry. Same way, the protein also has different effects. If say protein closes, then it will not work in your body anymore. That is how your metabolomics doesn't work, and you get cholesterol more, you get obese. But if your protein is folding is very good, protein folding is a different thing. All these things are worked using your NMR. Why? Because the signals what you get is not so simple, very crowded. So if you have crowding of the spectra, you don't use your 1 Tesla magnet, 2 Tesla magnet, because you use your 1 Tesla magnet, 2 Tesla magnet, you get a big hump, like big potato signal. There is no use at all, big hump. But when you remove the so-called your Boltzmann constant or Boltzmann's distribution by increasing the so-called energy difference, because it's under your control, nuclear-Zeeman interaction, increase your magnetic field, Larmor precision frequency. So easily you see that increase the magnetic field, precision also increases for a particular so-called nucleus. So you are increasing this. So thereby you can have a precise information. So that is how you get the idea, and you can solve a lot of problems. If a cholesterol is there in your body, you can identify each and everything, and you can in fact build a antigen or anti-material antidote for that, so that you can suppress that protein, causing the production of protein, cholesterol or any other thing. Same thing you can do. But for this, X-ray or any other can give you the structure, but dynamics is given by the NMR. And NMR is solving a bigger problem, that if your system is not crystalline, come to us, we will solve, but it will take time. And of course, with good amount of money in your pocket. So the thing is, what is NMR? You have a so-called degeneracy is removed. So you have this well-established technique is well-established. You see that. So all the signals, what you get, proton, carbon, everything is established. Proton 0 to 14 ppm, very much fixed. What kind of protons are there? Easily understood. Carbon 0 to 220 ppm. All this is well-established. Everything. Chemical shift. That is shift from the zero. Zero means what? It's not zero frequency. What is the base frequency? Just we spoke about when you take a proton, put in a magnet. 42.85 megahertz. This is your 42.85 megahertz if your magnetic field is 1 Tesla. Now why this shift is happening? Because in a race there will be a slow moving component, fast moving component, right? You don't have ideal situation, right? So this is slow moving component. So you have your downfield and upfield, all these shifts will be there. So why is downfield, upfield? Because your neighboring so-called your electrons are protecting. If your neighboring so-called shift can be understood from 0 to here, how much shift? I am talking about what kind of electrons are there. So I can talk about aromatic, aliphatic, all those things. Chemistry closely related to it. So anyway, spectral signature of the chemical group present, that is what we know. And Felix Bloch and Edward Purcell worked towards that. Richard got Nobel Prize in 1991. So this is a modern NMR spectrometer. Old NMR spectrometer looks like this. What do you require in so-called your NMR? Hardly Helmholtz coil configuration or solenoid coil configuration for your magnetic field. Okay, homogeneous magnetic field. Then your coil used for your samples. I think many people are browsing and cross-verifying whether what I talk is right. I can lit up. I can see their faces. It's lit up. Huh? So anyway, so they are cross-verifying that whatever I am speaking is right or wrong. Anyway, no problem. Okay. So what I mean to say here is, so here I have the different stages of the instruments. Very old, so-called instrument and new instrument. New instrument contains many features. Okay. NMR, the advanced version which even a layman can see the application is MRI. Not only you see the spectra, what NMR is giving is the NMR is giving your quantum mechanical information. Remember, it is a spin, nuclear spin is directly visible. Okay, directly visible. So no other spectroscopy, of course, other spectroscopy also gives, but here in NMR you can see the dynamics also. We will talk about the relaxation shortly. That is where paramagnetic NMR comes into picture. So these two gentlemen gave the idea of this magnetic resonance imaging, where each and every chemical shift will take the structure, but the effect of this so-called your spectra on any membrane or anything, you can view it through your contrast images. Okay, a dark spot on a X-ray and a white spot in a MRI is always a bad news. In hospital, people say, yeah, whenever you have a dark spot in a X-ray and a white spot on a so-called your MRI is always a bad news, or some information is given out through your so-called your MRI, magnetic resonance imaging, that can be done. Now, what is the well-established technique? Liquid is quite well established. You have a liquid, all the so-called molecules are rotating, tumbling, and giving an average effect. So it is giving a signal. It's easy to understand. So you have a modern spectrometers. You use pulse sequences given by Richard Ernst. The idea spin choreography, meaning that I put a pulse. Okay, I am not dwelling deep into the 90-degree pulse, whatever. It's takes time also. We give a small time delay which will be in microseconds, milliseconds. This microsecond, millisecond is the interaction time for each and every different interaction that we probe. If there is a nucleus, if there is an electron, both are producing magnetic field, how far they are producing. Okay. If there is a nucleus, there is an electron, there is another electron, there is another nucleus, how they talk. Yeah. If there is a nucleus and another nucleus, though they are seeing the electron, but I can talk through space. These are different interactions. If you have any other impurities, how can I talk to that? So these are different interactions which are in the NMR time scale. That time scale is captured by putting a small pulse and a delay. You change the delay, meaning now you know NMR is not straightforward. You should have a people sitting over there playing around with this pulse and delay. So all the other spectroscopic techniques, or so any other characterization technique, you have a fixed value of parameter. Okay, then you put it and you go off. Madhu used to make fun of me when I was in Bordeaux. Together we were working. So he used to fix a particular sample and come. We used to be roommates, and he used to say that you are still sleeping there only. You take the bed, go there and sleep, because we used to optimize the parameters there in MR, and we used to do it because the interaction time is all we require. This interaction time, where I switch on my pulses, where I switch off, and we have to design our experiment, because you have to make your nuclear spins dance according to your tune. Spin choreography, that is what I call, or we call in the NMR spin choreography. So that is how we extract, which it means that is a manipulation. No, not exactly, because you have a strong magnetic field that is there, which will not let you to manipulate. Very important. So you can be in the boundaries of the magnetic field and manipulate, but whatever resultant component is having all these notes. I told you, right, in a piano, you press all the keys, right? You have different frequencies. This is what you get, time domain signal. When you Fourier transform it, you get a FID. You Fourier transform it, FID is free induction decay. Why it is free? Because I am not applying any pulse. You are only detecting it. Preparation, application of pulse, detection. Preparation, application of pulse and detection. So you get the signal OH, CH2, CH3. And of course, you have a horrible spectra like this where you cannot detect, understand anything. You have to go for advanced experiments. Okay, spectral crowding happens. You apply different kind of pulse sequences where you can apply pulses for different channels together. Meaning, I am not taking only hydrogen at all. I am having hydrogen, I am talking to nitrogen also, I am talking to carbon also, and maybe oxygen also. I can decouple, meaning it's in your hand that you can decouple and couple the so-called interactions. So you bring in the interaction and finally you acquire, and you get a beautiful structure of correlation between H and N, correlation between C alpha, one type of carbon in a protein. So you can have a wonderful picture of mapping of what and where and how they are connected to each other. All this information can be got. So if you have a very protein structure, first what we do, you take a sample, you put in the magnet, you get a spectra, 1D spectra. We call it as one-dimensional spectra. Spectral crowding happens, you go for 2D, trying to connect between these two, other two, all those things, because it's under your control. What is under your control? Your pulse and delays. And pulse and delays, where you can switch off, where you can switch on, all these things you can do it. Because you can decouple also. Decouple means there's something two are coupled. So what you do is that you fix a frequency, 42.8 megahertz. Okay, you keep on shining, they will be busy, and the other one you can play around with that. So you can do a lot of things. Okay, so Gamberota, Giulio Gamberota, is I should mention every time wherever I speak. So in Italy is famous for only two things, good pizza, wine, and all those things. At the same time, mafia. Mafia is very famous, the birthplace of the Godfather, what we call. So there, cocaine industry is high, that is smuggling cocaine. So when you take cocaine and mix it with wine, you can't detect at all. So they used to smuggle this, but in NMR you can easily understand this. To take this guy, he is from Napoli, that is Naples in Italy. So he's famous for so-called your cocaine smuggling, because it's the seashore where you used to smuggle. Smuggling of people happens, smuggling of many things happens, cocaine also happens. And he is a very close friend of my supervisor, boss. We had met a couple of times, and he used to tell these very horrific stories where he did an experiment and 2 crore rupee in rupee was put on his head. If you bring this guy, we'll give you 2 crore rupees. The mafia had put a, okay, it's very scary, right? You did one experiment and published. So then, but he also knew what he was getting into. So anyway, this is in Italian. The narco people had a hit of so much big amount. Okay, he foils down the scanner. That is, he foils down the answer of like what is inside this wine. So you can see here simple 1D experiment of wine signal cocaine. Wine signal cocaine. So it looks like this. But cocaine with wine, which was completely not miscible, not available at all to see. So in NMR, it got hold of it. So anyway, he used to so-called roam around underground completely in US and all those things. In US also there were a lot of Italians. All those things were happened. But one particular big ring was put into Italy. Then he moved to Italy later. But still, he is living in scary situation. So anyway, NMR is such thing where you can discover so many things. NMR is that one. It is also applied for food industry, where you take a food or any oils or fats or minerals, you can use it and you can easily classify them. Okay, easily you can do it. Also RNA dynamics, all this can be done, high resolution. So when it comes to solution state, so many things can be done. Okay, protein structure can be solved and many things can be done. You can see the inhibition of a protein, exhibition of the protein, and you can control the disease control. You can discover new materials, all those things. But when it comes to so-called your solids, everything fails down again. Why? Because when you have solids, XRD peaks are available, superlattice, very good, very clear understanding, well understood. But when it is organic solid, which is amorphous, you see this is how it looks. XRD looks like this. Yeah, there is no information at all. So what do? You go for NMR. In NMR also is a problem. When you take this NMR solids, you get a big hump like this. It's not the resolution. Even if you go to very high resolution like 1 gigahertz, okay, 500 megahertz, something like that, still it is the same thing. So how you solve this problem? Okay, so very simple technique. In liquids, what is happening? In liquids, what is happening? We see into it. It's very old technique. 1940s is already developed. I'm just showing what is the difference between liquid state NMR and solid state NMR. Static solid, this is how it looks. You put a sample, it looks like this. It's horrible. You can't do anything. But in liquid, we have a mimicking of the motion. So that is, in liquids, rotating and tumbling have the averaging effect of the so-called your dipolar angle, dipolar moment. So that is one nucleus has effect on the other. Yeah. In liquids, they are too far off, right? Yes or no? But in solids, they are so close, they are packed. So one has another effect on the other. Zeeman interaction, inter-Zeeman interaction. So one makes the broadening of the other spectral lines. Because what is unique in NMR? Uniqueness about NMR is where I am with respect to the applied magnetic field with respect to the other guy. If the other guy is close by, he will also have the influence and have a broadening of the spectra, right? So that should be averaged out. So what do you do? So we take the sample, okay, bend it at a particular angle called as 3 cos square theta 1. I think KJM has already introduced this. I can see this 1 minus 3 cos square theta, something like that. I think he was trying to explain that. So 3 cos square theta minus 1 term, you make it to 0. What angle? Theta is equal to root of 1 by 3 or something like that. It is 54.74 degree using your Legendre polynomial. I think you might be aware of it. So Legendre polynomial P2 term is a dipolar term. So that averages to 0. So you take your sample and tilt at a magic angle. We call it as magic angle and rotate. Why rotate? Because we want to make the homogeneity of the spinning, just like mimicking the liquids. So when we do that, so this is how setup looks like that. How fast the spinning? You have to spin in such a way that proton and proton are so much away. Averaging effect happens 30 kilohertz, 20 kilo, more the better. So when I do that using a simple mass probe, magic angle spinning, magic angle is 54.7 degrees, spinning of that, okay, tilting and spinning. So when I have the stator and all those things, these are the rotors where I fill the samples and do it. So this is how it looks. See there? This is your static solid, this is your liquid state, but imagine your application is not in liquid mode. I want to apply in solid. Yeah, I will not go to liquid state NMR. I want to do the solid state NMR, but I want to have a positions. So then I start to spin. You see that? Almost close to that. These are the side bands. If I spin more faster, then I can get rid of this side bands. I can get the isotropic peak there easily. So there are different probes to measure X and Y. X can be carbon, Y can be nitrogen. All three can be measured together. All these things, mostly biomolecules, protein NMR for proton, carbon, nitrogen, okay, materials, glass zeolites, I have already told you, spin choreography. So you can decouple the interaction, you can bring back, all this can be done. So using your solid state NMR, again you can do. This is a two-dimension experiment where on one end I will put proton, another end and I can put carbon, and you get a matrix where what proton is connected to what carbon. The beautiful experiment where both of them evolve together. You decouple somewhere, you see that there is a decoupling happening on carbon channel, so that way here, and then again you can bring back and finally you measure it. So you have connection between sequential arrangement of pulses so as to capture the interaction time. So we can do a lot of things. So there are so many techniques that is developed. Now comes the exactly what I want to say to you is that when you have such kind of interaction, you can do so many things. Alzheimer, very famous problem, right? Alzheimer. It's a geriatric disease. As you grow old, you have the gray cells that is going off, drying off your brain. Okay, my grandfather, even my father started to develop that. Paralysis is starting to happen. So hyperintensities are very horrible cases, ischemia. So all these things are due to this Alzheimer. It's basically what is ischemia or these things? Protein starting to dry off with the water and sudden development of these tumors, all those things because of this one particular protein. So you can study these things in your solid state NMR. Great contribution from this 2002 paper. So this is solid state NMR. Okay. Not only that, you can have in situ NMR. Drosophila is a famous thing for your genetics people. Yeah, they kill Drosophila right and left. Fruit fly. Yeah. So they kill Drosophila like right left. They apply so many things. But in solid state NMR, the beauty was in I think 2014. So they took the Drosophila, put inside the rotor, spun it, did all the experiments whatever they want, opened it, it flew away. Okay, it was an amazing experiment. So ethically also they are good. They have no need of ethical clearance. Of course, they don't have any ethical clearance for Drosophila. They can kill. So okay, double standard. So that is different or triple standard. So whatever standard it is, but NMR gave an idea that you can put Drosophila inside, spin at 30 kilohertz. Can you imagine human being put in a particular thing and spun at 30 kilohertz per second? Yeah, 30 rotations per second, but it still can handle it. But humans also can handle because Sunita Williams is handling there in the so-called place, but not so much. But still, it can happen. So it's all about the frame of reference. If you see something rotating, spinning again, you have a psychological break. So same thing happens to that and it flew away. So you can do a lot of things. This is a solid state NMR again. So materials for the batteries and all. But now comes the point, my topic, that is paramagnetic NMR. Chemical shift, dipolar coupling, J coupling, quadrupolar, all are well explored. What is quadrupolar? When you have spin greater than 1 or greater than half, you have the spherical nature of the nucleus will turn to a oblate or prolate, and electric field gradient tensors will come into picture. Then that will screw up your so-called spectra. Information is lost. But when an unpaired electron comes into picture, what is the problem? Hyperfine interaction. Now remember, what is the main course of your NMR? Whenever there is a nucleus, when you apply a magnetic field, it gives you information. I am here. CH3, I am here. I am not changing at all. Whatever I add, nothing changes. This is the same thing. CH3 will always come in the one place. Okay, carbon of CH3, that is H3, also comes in the same place. No changes at all. No changes at all. CH2, CH3, OCH, everything is recorded, well documented. But when a hyperfine interaction comes, what will happen? So you have Fermi contact interaction and pseudo contact. I will not get into the details. What is exactly happening? Whenever you have unpaired electrons in carbon, hydrogen, everything is paired up. But when you have copper, nickel, transition metal, which is very, very crucial for your transport phenomena, electron transport phenomena, where you require your copper into your material for your application. But when I take the whole material to solid state NMR, what will happen? Okay, so total shift will be now diamagnetic shift plus Fermi contact and pseudo contact. So what will happen? This is what is happening. Have a look at it. This is very important slide. If I have a material like cyclam, cyclam is a small closed chain, okay, non-aromatic, okay, aliphatic material. So carbon, hydrogen, carbon, hydrogen. I have three kinds of carbon based on the frequencies of the. So I get three signals or two signals somewhere A, B, and C is deconvoluted. I know the shift. It will come in 0 to 220 ppm carbon. It's well established. Let's suppose in a materials you are working in materials, very functionalizing materials. You functionalize the material by putting carbon, copper. Copper has the unpaired electron. When I bring in, what will happen? Have a look at it. 0 to 220 ppm. 0 to 220 ppm. It is touching the fundamentals of NMR. It is breaking down the fundamentals of NMR. So when paramagnetic comes into picture, what is happening? It goes to minus 400, 200. We don't know. But here in this case, we know what is A, what is B, what is C. But when a small copper comes into picture, you see there, I brought in a copper. This is my model system, what I applied my so-called thesis upon. So you see there, all these. Not only this, I can't apply the routine techniques where I get information about proton, carbon, all those things. So what do? It's a big deal, okay? Paramagnetic NMR. So paramagnetic NMR is the picture where now the nucleus, whatever relaxation, that is we call it as relaxation. When I put energy, it goes to energy level, but it will not come back immediately, because I think yesterday Mallikarjuna was mentioning, sometimes it may take 30 days to come back. Phosphorus system, something like that. Normally it will be 1 second, 2 seconds, 3 seconds, more. Okay, but sometimes it is so slow, 20 days you have to wait to get one signal. Okay, there are cases because there are no available energies, because energy can be neither destroyed nor created, but only transformed from one form to another form, right? So energy also here, something is creation, something is destroying. So someone has to be readily available to take the energy. So that is called as relaxation. So here in this case, there are so many people to take the energy. So in paramagnetic, it is so fast relaxation, your broadening of the signal happens. So broad, it will be 20 kilohertz, 30 kilohertz broadening will happen. So it is so horrible that your base, what was your base? We know, everyone knows 0 to 220 ppm, carbon signal comes 0 to 14 ppm, proton signal comes, different aromatic, aldehydes, ketones, everyone is well established. But when copper comes, everything is completely gone. So we have to dig deep into quantum mechanical idea. So, but with experiments, we also saw that the disadvantage was turning into our advantage. What is the disadvantage? The proximity of this copper to whatever the system, okay, how far they are, how close they are, they had a pattern. The pattern is that closer the copper, so you had a far shift. Some of them which are there, okay, they were closer by. So you can see the broadening also, this is very close carbon, the other one is far carbon, the other one is farthest. So we had this correlation, means that any nucleus which is close to the copper or the paramagnetic ion had a broadening, very high broadening, this one, yeah. So which one is very farthest, which is this one, which was not so broadened. We are talking about the relaxation. So somewhere there was a relation that the paramagnetic NMR is a relation between the proximity of this so-called your copper and the any nucleus that is present somewhere. So it gives you a good correlation of the distances. We applied so many things. I was talking about the spinning. We spun to 30 kilohertz and we have a good resolution. So all these things we published in 2013, the paper and the thesis as well. So in copper and nickel, when I put nickel also spin 1, you see there how the things are happening, okay, how splitting is happening, all these things. But what was inevitable? Now quantum mechanics comes into picture. Quickly I'll finish off this one and come to the final conclusion. So what is so important is that not only shifts, chemical shifts, but I have a small S is what? S is a spin of the electron that is participating, paramagnetic. That's, for example, S is half means what? Only unpaired electron is 1. S is 1. What is S is equal to 1? S is 1. S is equal to 1. What is the meaning of S? S is the electron spin. If there are 2 unpaired electrons, S is equal to 1. Yeah. So 2 unpaired electrons in nickel. So S is equal to 2. So you can understand 4 unpaired electrons in high spin complex in iron and all those things. So you have this fixed constant, fixed material, magnetic moment, K is constant, gamma is nucleus aromatic ratio, T is temperature, Curie temperature. As temperature increases, Fermi contact shift is very, very less, it goes to 0. At zero temperature, Fermi contact shift is very high, infinite. So you can understand that very high temperature, the material is diamagnetic. Very high temperature, infinite temperature, So your Fermi contact shift is completely vanished, no paramagnetism. So you can have this, but A is the most crucial part. A is, you see all this constant, but then there is one thing called as quantum mechanical idea, rho of R. Rho of R is spin density. What is spin density? The spin density is the ability of this copper to migrate your electron to all the places in two processes. One is spin delocalization. You can localize the electron because electron is a quantum mechanical object. It can be found everywhere. Louis de Broglie's wave particle dualism, right? It can be found 0.1%, 20%, 30%, 40% everywhere. Yeah, you add up and you get what? 1. Odala? Yes or no? Bond's approximation. Yeah, integration of mod psi square is equal to 1. Yeah. What is the meaning? The meaning is that you add all of them and you have a probability of 1. So you add all of them and you get the unpaired electron as 1. So that is what is meaning half. So you get this. So if you want this, you are supposed to do the quantum chemical calculation. In the afternoon session, I am building the stage for my quantum chemical calculation. Gaussian. Gaussian is very, very essential. Still you can do good experiments using this, but everything is waste because my chemical information is gone. There is no chemical shift, 0 to 220 ppm, 0 to 14 ppm. The fundamental root of NMR is broken down by paramagnetism. But still have hopes, I have to calculate the chemical shift. My PhD was at stakes because I am doing NMR. I am doing experiment, very good experiment with very spin choreography and all those things, blah, 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 everything fine. But at the end of the day, people will ask, what is this carbon? Is this CH3, CH2, or what is this? At the end of the day, chemist will ask this, how do you do it? So we have to rely on so-called theoretical. So I did my theory, so-called your geometry optimization. I took a molecule, designed it, modeled it, and tried to optimize with the experiment because I have a good X-ray structure. I can do it. So finally calculated my frequency, whether optimization is right or wrong. I will be talking about in the afternoon session. You will also be having hands-on experience. It will not be only one way. It will be a dialogue, not a monologue. So we'll be doing together. So we'll be generating FTIR spectroscopy or spectrum together, and we'll be seeing the vibrations in hand quantum mechanically. All these things will be done. Okay, once this is okay, then this structure is okay. So then I went ahead and I calculated the shifts, diamagnetic shifts, that also can be done. So without any copper, how it looks. So this is how it looks. And then what I did was how my electron in copper cyclam was going ahead and seeing the spins density distributed over the complete molecule. This is how it looked. This is not an animation. This is the output of my calculation. So if you see here, the electron starts its journey, goes here, brings here, adds a small amount of magnetic field. That is the reason all the shift is extra shift, chemical shift plus paramagnetic shift. So when I know the spin density, if I visualize, meaning that is a calculation. If there is a calculation, I can visualize. Both can be done. So when I took this, you see here, diamagnetic shift is normal case. Normal NMR is done 31 ppm, 55 ppm. But you see here, Fermi contact shift, you add both of them, experimental and practical both matched, and that is how I can see. So where, how much amount. So DFT calculation is very much essential when you're using paramagnetic NMR. So you want to know where the electron contribution on different systems is there. So we applied for 2D. You do whatever you want now. So I can have the proton-carbon correlation. It is giving beautiful shifts and all. Of course, the interaction time is now dropped down from millisecond to microsecond because relaxation is fast. Okay, I have to design this. So I designed these experiments. All these things is done. So I have a beautiful correlation of this. I went ahead and also tried to see what is the type of proton is there, axial proton, equatorial proton, and all those things. So using your Karp-Plus relation, I don't want to get into details. And the beautiful part is that I can also correlate between proton and proton, how proton and proton are interacting. So this got published in one of the, I used to refer this particular book, Paramagnetic Solicited NMR of Materials. It's a famous book, pink colored book. My boss used to always give it to me, saying that you can refer to this, you can refer to this. After 4 years, my experiment, this particular experiment was cited here, and it is a proud feeling that, you know, one of the textbook is referring your work, and that was a proud moment where this is the first time in paramagnetic solicited NMR that proton-proton NMR was done. Hence, normally they don't put, it's very difficult. So they have this particular spectra, they're still in that book. So it was cited in 2017. So you can get that information. And of course, Curie's law, we refer to that also. Temperature variation, increase the temperature, shifts are increasing. This is a proof that it is a paramagnetic. So we also have done it. Applied it to various systems. So various systems like such things. So we applied to other systems also. It is published in 2013, but okay, we applied to various other systems also. So nickel also, but nickel there is a problem. I'll speak about it in the next session. So you can see here, what is the nature here? Can you see this? In copper, what is the electron? Where the electron is? If you are a spectroscopist or anyone. So what is this shape? Can you tell me what is this shape? Copper, transition metal, everyone knows, right? Transition metal group, D group elements, right? D, dxy, dyz, dxz, and then you have your dx square minus basic one. I am asking you very basic one. Dx square minus y square, dz square. Yeah, you see here copper. It is in dx square minus y square, one unpaired electron. Let's say, for example, I went and replaced that one with nickel. This is my output I got. Okay, this is the output I got. You see there, what is this? Dx square minus y square and z square both together, right? Two unpaired electrons in two. So we got this output. So you can understand through quantum mechanical. And one step ahead we went, and this was a wonderful thing. So we have something called a spectral density function in NMR, where a small relaxation is caused by your electron relaxation. R to the power 6 is the distance between the copper and where the nucleus is. If you measure the relaxation rate, you can connect nuclear relaxation rate, correlation time, and measure the distances. We have wonderful experiment with EPR combined, because EPR is electron paramagnetic resonance. So we measured it. If anyone wants the information, please come down, I'll talk to you. So XRD distances for this is see there, and in our case we measured the solid state NMR through this particular technique called matching with solid state NMR and EPR and this correlation time. So you can see with this is from NMR we got, converted it to distances and compared with XRD, and it is matching very well. So we applied to various systems like copper ACAC, that is acetyl. So mostly it looks like a chemistry thing, but it is purely physics what we are dealing with, quantum mechanical systems. Yeah. So we did, when I moved back to Alvas, we still had collaboration with my boss. So I had working on this experimental, but theoretical also I was working. So we applied for various other systems, which was quite interesting ones. So depth experiment was also done, again spin choreography. So background was cancelled, all those things can be done. So if you see there, proton NMR, carbon proton should lie between 0 to 14 ppm. See there, you have this small 0 to 14 ppm, still small diamagnetic component is still there. But paramagnetic is so large is that 50, 100, 150. Proton will never come to 150, remember. The maximum it will come to 0 to 14 ppm. This is your diamagnetic. So you can't apply NMR anymore. It will show, but it is just a showpiece that you have got a proton NMR in paramagnetic, but I cannot assign. So we don't know exactly with the conventional technique fails. So carbon also same way. 0 to 220 ppm, only this much is the diamagnetic NMR or the well-known conventional technique. But now I have so many things. So this was published. So again same technique, DFT calculation is very, very crucial. And yeah, so I will be talking about DFT calculation. These are all theoretical simulations that we have got. So we can generate it, we can calculate, do the calculation. So anyway, I just applied to different systems. So we applied the same thing to your materials like vialogens. So we applied to that also. Vialogens are the materials where you apply pressure and it changes the color. It is used in your conductor receipt who gives in your so-called printer. No, he has a small thing where he prints a ticket. Yeah, have you taken that ticket and try to press it? It will create some color. No, that is, those are vialogens. This is application. Yeah, in your ticket, that is what you call, have your small machine, right? So that roller, what you have, the receipt, whatever roll, paper roll, that is vialogen material that is been put onto it. So when you put pressure, it will change the color. That's again paramagnetic. So I applied to the so-called lithium manganese cobalt oxide, again material, battery materials. I did postdoc in ICMCB Bordeaux. We come to the end of this session. So changing of this form from one form to another form. Of course, lithium battery is well established thing, very commercially good. But when sodium comes into picture, cost effectiveness is crucial. But when you go to XRD, it gives a lot of information, true, but dynamics is very crucial. When you desodiate or sodiate any material, okay, so you put sodium and remove sodium, that is what is the whole process of battery. So you change the so-called stoichiometry, it changes from one form to another form. That also can be closely monitored using NMR. So this is your JIT. I think everyone uses this JIT, I guess, for so-called changing the different systems or the phases, different phases from O to P, okay, octahedral to so-called your prismatic and all. So now NMR also can be seen that structural variation is happening. So we published result in that. It's still going on, but this particular thing is a wonderful result. So again, this using a different simulation package. Again, paramagnetic NMR. Okay, shifts are very essential. You see there again, they're also doing the shift calculation, not organic but inorganic systems. You see there, sodium is there, oxygen is there, nickel is there. Nickel is paramagnetic. Okay, when a free electron comes, then it is a problem. Whatever sodium NMR is well established, everyone knows. But here, when nickel comes, there is no use of NMR. So you have to calculate spin density. Again, we have to calculate spin density, and we have done it. And there is another part of paramagnetism, it's called as polyparamagnetism, gives rise to shifts. And shift is not in 1 kilohertz, 2 kilohertz, not even 100 kilohertz. It is 1 megahertz. So you can have change in frequency. You remember what is the frequency of proton? 42.8 megahertz. When lithium comes into picture, it will change to 45 megahertz. So large interaction. So that polyparamagnetism also I have studied. We are measuring tin NMR, purely on tin NMR. So tin NMR gives you the idea, dynamics can be understood, lithium tin system. So in Ohio State University. Later on, when I came back to Alva's, worked purely on theoretical. So using polymers, and chitin was the base. So we optimized structure using NMR. Using the DFT calculation we studied, and we progressed in that. So this is most cited one so far whatever done work. So DFT calculation will be followed by. The overall conclusion is that paramagnetic NMR you have to use this, and DFT calculation is inevitable, because the fiend or the party pooper, what you call the unpaired electron, is the one which messes up the whole conventional technique. Conventional technique drops down like anything. So you have to have DFT calculation to understand the whole the network of it. Otherwise, whatever you measure or whatever you take the data from solid state NMR, where people want to apply your whole system into a solid mode, then you have to have DFT calculation. That is the whole idea. This is our group. Anyway, I will be talking about this later. So anyway, if I want, we obtained a VGST project, and we obtained this with these results. In 2020, we obtained this. We procured these instruments and all based on that fund. We also have the EFNMR, Earth field NMR, where you can put this is a capsicum, bell pepper. We can have the cross section of the bell pepper with the earth field NMR, MRI. This is your orange. There's layers of oranges. Without peeling it, we can have a cross sectional area. There is no magnetic field. No magnetic field is Earth's magnetic field, 42.5 micro Tesla, not even 1 Tesla. Okay, million times lesser than the. So magnetic field is crucial, but how? But how is this? You can talk to me. I will tell you about it. So Gaussian workshop was done during that era, that time, 24 years back. So simulations I use from all the way from home, that is South Canada, to Lumo, where I did my PhD. Still I'm in touch with them. So we run this cluster. Solid state NMR lab is here, and just above that we are having cluster. That is where we put the calculations. So this is my boss, Professor Jan Sitma, still in touch with me. So we have worked on various systems and all. So recently, 2024, I think 9th December, we got this published on nonlinear optic materials. So we use this as a regular thing. It's a very well established things, but we want to explore more novelty. So this is again DFT calculation. I do DFT calculation. If someone is interested, we can do. Afternoon, we have a session on DFT calculation, hands-on experience. Okay, it will be more dialogue. Small molecules we have done. This is with Rumana and all the groups. Okay, thanks to Krishnavani madam. So I did DFT calculation on this, homo-lumo calculation, all those things we can establish. And this is the one polymers. Polymer is a very difficult one, because polymer molecular weight is 2 lakh, 3 lakh. But still, that one paper where I showed chitin, we had a strong hunch that we can write a word called as monomer approximation. I was speaking about that, right? Monomer approximation means we use a single unit of chitin, and we publish the results. But reviewer asked, how dare you use monomer approximation? We gave you the clear details to them. They were happy, and that paper followed. And again, we started to use the same monomer approximation, because normally in polymers you don't have any single chain like this. Okay, we have lakhs together. So I try to build only one chain. This particular so-called calculation miserably failed after 6 months. After 6 months of running of calculation with 16 node. Normally with your computer it takes 15 years. But with my cluster, it took 6 months. with this, but miserably failed. So we adopted a new technique where we started to substitute different, and we have a publication based on that. That publication followed up another publication in applied polymer science. So yeah, same thing. So all these publications are paramagnetic NMR and DFT calculation. So we have instruments back in our lab. So we have keyless digital source meter, and we have variable temperature UV. Okay, you have your glove box for so-called inert atmosphere, all those things. I think 20 minutes ahead, I guess. So I'll shortly finish off. I have Alpha 2 FTIR spectrometer, and this is a small group where we were working in an group in Ohio State University. There was a professor in Ohio State University. I was talking about grandinity, and Danny Kerlier. I think Madhu also knows her. So this is my postdoc boss, PhD boss. This is Richard Ernst, another NMR specialist in India. Professor Anil Kumar recently passed away. So I had an opportunity to go to an NMR center because of this personality, Dr. Ramkrishna Damle. He is my teacher to inspire me to go in NMR. So yes, again we have a lot of collaborators. Of course, Madam is also there, and Gurumurthy sir. We have the collaborators. So thanks for your attention. If you have any questions. One question there. Yes, sir. Yes, sir. What do you mean by DFT calculation? Gaussian. Gaussian is called as isolated gaseous state approximation. Yes. No, gas phase. 0 Kelvin calculation. But remember, two words are there. Isolated gaseous state approximation, meaning you treat your molecule as a single gas entity. Okay. When you go to WASP, Vienna ab initio simulation package, then Wien2K, quantum espresso, it is solids. It's called as PBC calculation, periodic boundary condition, meaning you are close to reality. But good thing about Gaussian is, that's what, approximation comes into picture. 0 Kelvin calculation means, what is the meaning of 0 Kelvin? You don't reach to 0 Kelvin, right? Minus 269 degrees Celsius. Minus 269 degrees Celsius is not reachable position, right? So 0 Kelvin is very, very hard. 0 Kelvin. So you can understand 0 Kelvin is very, very difficult to reach. So which means that where dynamics stop. So everything is solid. That is where Gaussian seems to be working out. So everything is fine. But this whole things breaks down when you have a spin correlated system. When you have an unpaired electron and another unpaired electron close by. So that's the reason we use only one cluster. So inter will be difficult. If you have two copper cyclone structures close by, this so-called nucleus and this electron is closely related. It's called a spin correlated system, where most of the, I think, Madhu's work, magnetic properties, they are very aligned together. Heisenberg spins antarala. So they are very difficult to do in DFT. Even DFT fails. So when you talk about these solids, there are different simulation packages. I worked with WASP also. Correct. Surely difference. Now you see there, for example, insulators, right? What are insulators? There is always a gap between one electron to another electron, right? Your energy gap is high. What do you consider as a insulator? Energy gap wise, anything which is greater than 3 electron volt, something like that, is more than that, 10 electron volt, 18 electron volt. So when you are having too much far off molecule, you can easily say to a reviewer or anyone to convince saying that one system is not affecting the other. What is the whole idea of paramagnetic system? Copper is there. Let us speak in a very simple fashion. You will also understand. When I have an electron, it will jump to this. How far it can jump? It can jump and it can be in the molecule, right? But if you want to go to another molecule, it has to be close by. Yeah? If you use insulator, approximation is good. But if you use a metals or something which is close by, which is called as PBC, which is ordered crystalline, it doesn't work. Gaussian doesn't work. That's the reason we give an idea. Isolated gaseous state approximation. Yes. Metal organics. No, that's what I'm saying. It is metal is there, but organic arm is also there, no? The counter ions are moving counter ions. That's the reason we carefully selected the system in such a way that they are far off. They are no more metals. Even though there is a metal, There is no another metal to talk to, right? They're insulators. This is a metal. I totally agree. What is a metal? Yes. Why? Did you see the structure? How far the distance between the copper and another copper or whatever metal you're seeing? What is distance? That is good. I am talking about 7 angstrom, 10 angstrom distance. Are you understanding it? So, the distance between two, you should not make them meet to each other. So, this is the whole idea. If you have, that's what I said. This word is called, you can search down. It is well established. It's written, a lot of papers are spin uncorrelated. Spin correlated, you are talking about spin correlated system. When you have spin correlation, one atom which is having unpaired electron or metal is contacted with another one very close by. When you have 5 angstrom, still contacted. So we can speak, no problem. We can speak, I'll give you the examples. So, but if you are dealing with solids, then of course this one will miserably fail. So we have to go for something else. That's the question. Yes. Correct. We don't have control over it, but we have polarization coil. Just like you have a small ant. If I want to see that ant, I can see through my eyes, but I use a lens. So I magnify it. So I have a polarizing coil. A momentary magnetic field can be given so that I can amplify just like an amplifier. I have a signals. That's very small signal. I can amplify the signal for polarizing coil. That can be done. There are no questions. Okay. So nice. Thank you. Thank you. Thank you. Now let us break for